Okay, so we'll talk about cross-validation, and then we'll talk about Bootstrap. And so, and I'll pull out the pen for these things. Cross-validation. I mean, it almost feels a little premature to talk about this, but I think it's okay. In your regression class, have you created a basic linear regression model yet? Yeah. Okay. So we can at least have some context here. With cross-validation, a lot of times you've got to, well, even before we talk about cross-validation, a lot of times you've got some kind of data and you're trying to fit some kind of model to it, right? And then sometimes with your entire data set, you might split your data between a training data set and a test data set, okay? And the idea there is in order to evaluate how good your model is, you don't want to just fit all of your data all at once. Because if you fit all of your data and you fit like the perfect model, you have no way to see if it's actually good, because maybe you're, this is a ridiculous case, but it's possible to create a super, super, super complex model that fits your current data set perfectly, right? And you've got maybe 200 points in your current data set. This would be a small one. Maybe you have 200 points in your current data set, and you created this really complex model that says, if the person brushed their teeth and wore a pink shirt, they are going to purchase this product, okay? Because that's what happened in our data set. And so we're going to put that in our model, and we're going to say, person was, brushed their teeth and wore a pink shirt, they're going to buy this product. And then obviously, in the future, you find another person who brushed their teeth and wore a pink shirt, and they didn't buy the product, and then your entire model falls apart because you made your model too specific based on your current data set. So what we often do is we will split our data into a training set and a test set. And we use the training set to kind of create a model that is hopefully not too specific, but specific enough to model the features of our training data set. And then we run the same model on our test data set. The test data set has the predictors and the answer. And then we throw the predictors into the model. The model says, I predict this, I predict this, I predict this. And we compare those predictions to the answers, okay? And we'll have some kind of metric to say, oh, these were good predictions or these were bad predictions, okay? And the idea being that you can, based on your training data, you can create a model that's going to make good predictions on the test data. And if the model works well on the test data, or almost as well on the test data as it did on the training data, then you might be satisfied with the model that you've created. Okay, so let me kind of say this is all right. So we often start off with this will be our data. Why is my cursor all? I don't know what my cursor looks like this. Okay, and then we'll kind of draw some kind of line here, and then we'll split it into train and test. Okay, and then we create the model. Based on this. Oh dear. Okay, hang on. My computer is acting funny. close some applications. Okay, and then, okay, so we create this thing, and the model is our model, okay? And then, so the test is, the test gets split into the predictors, okay, and those go into the model, okay? And then the model spits out predictions. Okay, and then what we do is we compare our predictions versus the actual answers. Okay, and then we throw this into an error metric. Okay, this is how we define whether or not our model is a good fit. Okay, and so a very common one is the, or we might call this a loss function, error metric, or loss function, or something. We want to minimize the difference between our predictions and the actual answers. Okay, and so a common choice for numeric values is the mean squared error. Okay, or you might have the root mean square error. Okay, and so the mean square error is basically you're just taking the difference between each actual value y, you're subtracting off the prediction y hat, and then you square that difference. This is the prediction. And then, you know, you sum this up over 1 over n. Okay, so that's what we do. Okay, so there's all sorts of questions on how should we split our data into training and test things, right? Because you know, you create a model and then maybe you have competing models, right? So you have model 1, but then you could also have model 2, where you have you know, and then or you have model 3, and you can run all of them through here, and you know, you want to know, okay, well, which model is the best, okay? And you know, you want to pick. There's a balance between you know, the complexity of the model you want, and you know, how accurate your model is, right? You might be able to get even with your training and test data, because of, you know, coincidences and whatnot, you might be able to create a really accurate model that is just maybe way too complex for its own good. Okay, and so, you know, these are the questions here. Okay, so the example we're going to use to kind of illustrate these different cross-validation methods will be, we're going to look at this auto data, automobile data, and there's all sorts of variables in auto. So maybe here, I'll start our script here, because not all of this is in there. But so you're going to load up library ISLR, okay? And if you haven't installed it, you're going to have to install it. Okay, and then we're going to do data auto, right? So we load up auto, and we can take a look at the the head of the auto. Okay, so auto has several variables. Okay, MPG, cylinders, displacement, horsepower, weight, acceleration, year, and origin, and the name. Okay, and so we'll look at the names of auto, and all we're going to try to do is see, is there a relationship between the horsepower of a vehicle and its gas mileage. Okay, so just we'll create a very quick plot. We'll say, is there plot auto and horsepower versus auto and MPG. Okay, so when I create this plot, this is, let's make this bigger. Okay, and there definitely seems to be some kind of relationship. Something, my computer just froze on me, I think, or at least this plot window did. Okay, well, there definitely looks like a relationship. There's a negative relationship. The cars with greater horsepower get less gas mileage. Okay, and the cars with lower horsepower get more gas mileage. That's what we see. This data set's a little bit older. We've much improved vehicle efficiency, right? It's very common to have a vehicle with 200 horsepower these days that get 25, 30 miles per gallon or something. But back when this data set was made, if your car had 200 horsepower, that was probably like a sporty car, and you would get 10 miles per gallon or something. But that was the cost of your fancy vehicle. And then you would have to, if you wanted high mileage, you'd have to get the 50 horsepower vehicle. I don't think there's a single car on the market that with 50 horsepowers today. Okay, my computer has frozen. Let me,